That's why the O has that. That's normally the German. Okay, Grobner basis. Right? Okay, you need to have some kind of reference books. Okay, don't depend totally on my notes. I have mentioned this in the earlier class. Okay, there are quite a number of group theory books that is available online. Okay, so the Grobner basis, there are primarily defined 4 ideals in a polynomial ring. So suppose we have polynomial ring. So if say we have a polynomial ring over a field K, right? Now I mentioned field, you have to know what a field is. And polynomial will have the unknown, right? So suppose we have this a polynomial ring. Okay, suppose we have this a polynomial ring. Then we need to have some definition, right? Before I go into Grobner basis. If you remember, Dr. Sanhan shared quite a number of definitions in his notes. Okay, definition, I call it 11 point, right? Algebraic variety. Okay, so we need a subset, a finite subset. Of this. Okay, then the algebraic variety, not verity, yeah, variety, call it VS of Fn, right? Is the set of all common zeros. Common zeros in Fn. Okay, in Fn of the polynomials in S. Okay, what does it mean? Doesn't make sense? Okay, so you see, this is a polynomial in a ring, right? And let's see. S is a finite subset of the polynomial ring, meaning there is a subset S, and inside S, it consists of polynomials, okay, polynomials. And the algebraic variety, we call it V of that S. Now it's in Fn. It's in Fn. It's the set of all common zeros. Zeros means the root, right? Okay. Okay, the root, the set of all common zeros of the polynomials in S. So inside S, there are polynomials. So let's see example. Okay. So example 11.1. Okay, let me give this here. Okay, so example 11.1. We have a set S in Rxy. Okay, S in Rxy. So S is, the first polynomial is 2x plus y minus 2. Okay, I just give now just one. Inside, which is a subset of Rxy. This is only one. Okay, there's only one. Now, there's only one polynomial. The 0, there's no common, just one. So the 0 is the set where this is equal to 0. So when it is equal to 0, and since this is xy, this n is the number of finite subset of this. So that is an f1, f2 until depending on how many in this. So this n depending on this, right? So our answer will be in xy, n equals 2. Right, so let's find the algebraic variety of this. Okay, so 2x plus y minus 2 equals 0, or you can get y equal negative 2x plus 2. So the zeros will be all x and y. That, so we have like this, right? When y is 0, x is 1. When y is when x is 0, y is 2. So we put there that it's a line with the x-intercept 1 and y-intercept 2. So that is the algebraic variety. So we can write also v of s equal xy in R2, y is negative 2x plus 2. So this is one example. All right. Okay, so if you extend, you have so many polynomials. So to find the variety, the algebraic variety, then you have to have system of linear equation. So if there are many of them, you have to find the common zeros. If you have like the first one, the second one, the third one, you have to solve the equation. Okay. All right. Now the next one, the next one is the, okay, wait a second, basis, right? The basis for the ideal. I don't know why my computer is like very, very slow. Maybe too tired. You know, 2 days ago, I was like typing everything, suddenly it hang. I had to retype everything. Okay. All right. Okay. Okay. Now, okay. basis for an ideal. All right, so you remember ideal, the definition of ideal? Can somebody tell me what's the definition of an ideal? An is a subset of n, or
NB subset of
n. Okay, for all, for
AB belong of ring.
yeah, A and B is element of the ring, and n, what is n? N is a subset of the ring.
Yes.
Okay, subset of the ring. Okay, so let I be an ideal. Okay, let I be an ideal of a commutative ring. So we want only of a commutative ring. So if you're working with a ring which is not commutative, you cannot use this definition. Yeah, because we want also to have a unity. Okay, now we want a subset. We want a subset to be a basis. You remember the last time we mentioned about the free group, right? And free abelian group with a basis. Now, a subset, we want to use B1, B2 until Bn. Okay, a subset B1, B2 until Bn of I is a basis. Is a basis if I is generated by this. Okay. So it span the whole thing of I, and the linearly independence is embedded in here. Now look at the theorem. Okay, the set of common zeros in a set of polynomial rings is the set of common zeros in the ideal generated by the polynomial. So this is a basis for finding the Grobner basis. I'm not gonna prove this theorem, but if you are given a polynomial ring, if you are given the polynomials f1 through fn, and you are given that these polynomials span the ideal given, okay? Now they give the same set of common zeros. Okay, and the Hilbert, there is a Hilbert basis theorem. Okay, theorem 11.2, Hilbert basis theorem. Every ideal has a finite basis. Okay, every ideal has a finite basis. And I mentioned earlier about ideal, right? I is a subset, right? If the whole ring, oh sorry, we use n, right? Well, if you, before I just use a n, but if you want to use I, you have this, right? For ideal. So not all subset is an ideal. sometimes when you multiply, this means if R in I, right, AR is in I. Sometimes when you multiply with R outside, it goes outside. Okay, in that case, it's not an ideal. So you have to check for this one. So the objective of this theorem is to find a basis for a given an ideal. And with this basis, you don't need the very long sets of elements. With just this basis, you can just span. You can just span the whole structure of the ideal. All right. Okay, now this is very important. You have learned this before, but I will write it again as a review. I'm sure everybody has seen this from high school. Okay, so property of the division algorithm. Property of the division algorithm. All right, so now you have a polynomial, ring polynomial. So suppose you have polynomial in this ring polynomials in terms of x, and suppose you have fx. What do I use? Fx, gx, quotient of x, and remainder of x. Okay, so suppose these are all polynomials in the polynomial rings. And you can write fx equal gx times rx plus, plus rx. Fx equal gx times qx plus rx. Quotient and remainder. Yeah, quotient and remainder. Okay, now this property of division algorithm said that the common zeros of fx and gx are the same as the common zeros of gx and rx. Okay, the common zeros of fx and gx are the same as the common zero of gx and rx, common zeros. So you reduce the more complicated polynomial into a simpler one, and then you find the common zero. Okay, and also let me write the common zero, the common zeros in Fn, okay, of Fx and Gx are the same as the common zeros of Gx and Rx. Okay, also the common divisor. So the common divisors in Fx of Fx and Gx are the same as the common divisors of gx and rx. Okay, you can go through the proof and see what do you mean by a common zero. C is a common zero of Px if Pc equals 0, right? That's mentioned in Dr. Sanhan's lecture last time. So, let me write. Now, if we have, say, fx equal gx dot qx plus rx. Okay, now suppose A is a common zero. Suppose A is a common zero of gx and rx. Okay, so what is f of A? So this means GA is RA is 0. You see? So FA is GA QA plus RA. GA 0, RA 0. So you see FA is also 0. All right. So since this is already there, so it's also a 0 for FA and also a 0 for GA. Yeah, so the proof is actually really straightforward. You can go through and see the other way around. Okay. Now we are ready to talk about Grobner basis, right? So this chapter actually is all about polynomials and you have to know how to divide polynomials. Okay, let's try one polynomial. Now I just come out with this now, yeah? Let fx equal 4x cubed. Oops. Okay. I have to make sure that my students are here, not me talking by myself. And suddenly the Zoom is out and because I normally don't look at my phone. So if you send me a message, if you need to interrupt me, you have to turn on the mic. Yeah, just turn on the mic. Interrupt. Don't message. Don't chat because I don't look. Okay, so okay, so this I want to say that our polynomial is in maybe I put 6, yeah? Yeah. The ring is Z6, okay? The ring is Z6. What did I put this? The ring is Z6. And this is in terms of x, yeah? Okay, the polynomial ring of Z6. And I want the gx equal x plus 1. Okay. find Qx and Rx. I give you 2-3 minutes. So what you have to do is you have to do the long division, yeah? Right? Try to do long division. 4x cubed plus 2x squared plus 3 divide by x plus 1. Whatever on top will be the qx. Whatever the remainder will be the rx. Okay. 3 minutes.
Finish, Prof.
Finish. Okay. That's how you do it. You just turn on your mic otherwise. All right. So let's try. Okay. I have to bring it up. So you divide this by the first, right? You get
4x squared.
4x squared. Okay, then you multiply that.
Multiply, yes.
What? 4x cubed
Square.
4x squared. All right. Then you substitute.
Minus. Yes.
Okay. So 2 minus 4?
Minus 4x squared.
Okay. Plus?
Plus 3.
Okay. Actually, there is no minus 2, but at this point, it's okay. Minus 2?
2x minus 2x.
What is it? That's now z5, right? All right. So minus 2x, right? Minus 2x squared divided by x minus 2x squared minus 2x.
Yes.
So I better put this over here, right? Okay.
Change the sign.
Okay. So 2x
Plus
plus 3. So plus
2.
2x over x plus 2 multiplied by 2x plus 2.
Plus 2.
So you have 1.
Yes.
1. So you will write like this. You will write
Ux
4x cubed plus 2x squared plus 3 is equal to x plus 1, 4x squared minus 2x plus 2
plus 1.
1. Okay, so this is the long division. So you will know that there is a remainder. If there is no remainder, meaning you can factor completely, so you can find the 0, right? by x plus 1 equals 0. Okay, now this is just to see whether you still remember the long division. If the answer anywhere, but this is not really correct because we are in Z5. In Z5, you don't have -2. What is -2 in Z5? 3, right? -2 is +3, right? Why? Since 3 plus 2 is 0. Right? It's the inverse. Yeah, -2 is the inverse of 2, which is 3, because 2 plus 3 is 0 in Z5. So you have to write your answer with the coefficient in Z5. Don't forget. Okay. Any question?
Prof,
Yeah.
Z5 not contain minus and plus,
Yeah.
all number.
Yeah. Z5 only contain this. So you cannot put negative as your answer. When you do calculation, it is okay. That is exist, but in another way. We call it another way, right? So you have oops, or is it a lot? All right, so 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? Or you go 0, -1, -2, -3, -4, -5. So, but we just leave it as 0, 1, 2, 3, 4. All right, and B is a negative of A, B is a negative of A if and only if A plus B is 0, which is a multiple of 5, right? So that's why you have this. Okay, so leave your answer as positive. Right. Okay. Now we go back to the notes and we define Grobner basis. This chapter is actually quite interesting because it all deals with polynomial. Okay? Oh, I don't want many. I want one this Grobner basis. Okay, so I want to make sure that I use the same symbols. So a set G1, G2. I want to have R polynomials. And I don't want any 0. Okay, no 0 polynomials in this. Okay, f of x1 until xr. Now, this is the new one with the term ordering. With the term ordering, this I will explain what it means by that ordering in Grobner basis for the ideal I generated by G1, G2, G, what do I call it? R. I didn't give you the ideal, but let's say this ideal is generated by this G1 until GR. Okay. Is if and only if that exists for each non-zero F, for each non-zero F in the ideal. Okay, there is an I in between this, such that this 1 times P of GI divides 1 P of F. I will explain about this with an example. Okay, first, this is a polynomial of degree 1, yeah, and this term ordering it depends on what the term ordering means. If I said X is less than Y, so when you order X is less than Y, X and XY on the right. Okay. How do you order if X is less than Y? So you have, which one is, you have this, X is less than X squared, right? X is less than X squared. And when you multiply by Y, okay, definitely you know, because Y is bigger, then you know how you go to the right. So this is how you order the order of X and Y. When we reach to this in example, I will let you know. Okay, now let me give directly as one example, yeah? Okay. Okay, now the question is, by using long division like before, I call this example 11 point. Reduce the basis. Reduce the basis. XY squared Y squared minus Y for this ideal. I generated by XY squared, Y squared minus Y. Okay, and the polynomial ring is in terms of real with X1. So it's under real, and with the ordering, we call it order lex Y less than X. Okay, so that's how you order Y, then X, then maybe x squared, then yx, and so forth. Okay. Now try and divide. Okay, now you see this and this and this, you can divide, right? You can divide, right? So what you do is you divide. If you can divide, so you will put xy squared, y squared minus y. So this divided by that is x, right? Then you multiply, you get xy squared minus xy. And you subtract, you get xy. Now this you cannot divide by this. You cannot divide. Okay, this is y squared. Okay, y squared does not divide xy. So we cannot continue this division. Okay, and when I said just now that for this one and you compare with this one, right? Xy and y squared minus 1, then we don't have anything less. So we have already a basis of this will be xy, and so we have to reduce this basis to xy and y squared minus 1. In a way, from this one, you can take y out. From this one, you can take y out, y minus 1. So that's how you will get this back to xy squared. This is, if you think this similarly to vector space last time, if you have a basis more than you need, you can just disregard or reduce the basis. For example, if you have a basis like x plus 1 and 2x plus 2, and you generate this, right? This is just a multiple of this, right? So this is the same thing as when you generate this, basis is the same as just this. So it has a similar idea, because this is the same, and this is just 2 times this, right? So the same thing as here, you cannot reduce anymore. So you just take this xy and the quotient. So they generate the same ideal, right? So this is an example. Right, let's try maybe one more. Okay, this one more, right? Yep, 11.3. Okay, 11.3 is it I equal x squared y minus 2, and then x y squared minus 1. Okay, now what happened if you cannot divide using long division, right? You cannot divide using long division. This one has more x, this one has more y. If you want to divide this by this, this has more x. If you want to divide this by this has more y. So what we do is we want to simplify, and what we do is we multiply one side by y, we multiply one side by x. So I multiply this by y, okay, and then I want to get rid of the first one. I multiply this one by x. So this is the rule. Once you cannot do long division, you multiply by the x of y to get rid of one of the term, okay? And this one you get x squared y squared minus 2y minus x squared y squared plus xy. So this is equal to xy minus 2y. Okay. Now, the original x squared y minus 2 and xy squared minus y. Now this one, you see, when you do this, you see that this is called the leading power product. Okay. The leading power product xy is not divisible by either this one or this one. Okay, so in original definition of the Grobner basis, we cannot reduce anymore accordingly to the definition. So this one, this is actually not a Grobner basis. Okay, according to the definition 11.3. That is the definition just now, 11.3. So when you do the PGI and PF, okay, you will see that this leading one is not divisible by the other these two. The one that I put like before, 1 dot p of xy is not less than 1 dot p of xy squared. And it's not less than. It has to be one is less than the other one. Okay. Now, what we can do if you are given a basis, and if you are given already a Grobner basis or some ideal, or you want to show that something is a Grobner basis, the easiest way is to use theorem 11.4. Okay, 11.4 says if you have a polynomial, you can reduce to 0 by dividing and dividing by the remainder. In the division algorithm that we do before, if you can do that, then you can show it's a Grobner basis. So theorem 11.4 is one of the easiest way to show that a basis is a Grobner basis. Okay, let's try that. Okay. Okay. All right. So, example 11. So your task now is to, I skipped some of things, but because I want you to try and understand from the reference book that I asked you to at least find. Okay, what you have to do is to read through this section from the beginning to understand what it means by the leading one, to understand what it means by the legs, the y less than x, okay? And Shiham, actually, this is something to do also with all the words and alphabets and from the free basis. So go back and try to see from the very beginning when I mentioned about the legs, okay? The order of the x and y. It's quite simple. What do you mean by 1 times PF is less than the other one, 1 times GXI? All right. I will show another example, 11.4. Now, suppose you have this 2 polynomial. G1 is equal to x squared y minus 2. G2 is equal to xy squared minus y. Okay, and I is the ideal generated by these two G1 and G2. Okay, from the previous example, we have seen that we reduce that to this, right? We reduce these two because we cannot divide, and we reach to this one, xy minus 2. Okay, this one cannot be reduced to 0, right? So we obtain this polynomial from these two. We cannot reduce this to 0. Now we will put them together. We will put these three together, and you see how we can reduce to 0. Okay, when we put them together, then we can reduce that. Okay, so let's put this all three together. X squared y minus 2, xy squared minus y, and then xy minus 2y. Okay, this is what we call the augmented basis. In your question, you won't be given this. You will be given just these two. But with these two, you cannot do any further because you cannot do long division. So what we did before is we multiply this by y, we multiply this by x, and then we reduce. Okay, if we stop just by this, we don't get a Grobner basis. We cannot reduce to 0. Now, the next step to get a Grobner basis is to put all of them together. Okay, so try to reduce one by one term until we get to 0. So what we do is, how do you get rid of this? How do you get rid of this? By this. So what I do is, I will write like this: negative x third plus first. Negative x third plus first. So this I will get, right? I multiply negative x by this, right? And then I add to the first. What do you get? You will get 0, right? 2xy minus 2. Then you copy the second one, xy squared minus y. Wait a second. Okay. So again, this multiply this by negative x. So negative x squared y plus 2xy. Then add to the first. This. So negative x squared y plus 2x plus x squared y minus 2. So this and this. Okay. So 2xy minus 2. Just copy xy minus 2y. Okay. Then you want to get rid of 2xy. Okay, you want to get rid of 2xy. So what you can do is you multiply the third by negative y. You want to get rid of this. Okay, so you multiply the third by negative y plus the second. All right, okay, so when you multiply this by negative y, you get negative xy squared plus 2y squared. Okay, now copy 2xy minus 2, 0, right? And then 2y squared minus 1. And then copy xy minus 2y. Okay, at least you reduce it a bit. Okay, now you want to reduce the power, you don't want any square or anything. So how do you get rid of this? You see this and this, right? So if you multiply this by negative y, right? You multiply by negative y. Multiply this by negative y, then you add to the second one. Try it. Just y, right? Okay, so okay, so you will get multiply y. So you get xy squared minus 2y squared. So you will get, oh, sorry, 2xy minus 2y, oops, I already add. Then xy squared minus y, xy minus 2y. Is that right? I want to get rid of the xy squared. What happened? Yeah, so I get 2y squared minus y. That's right. Oh, sorry. This one, no. This one is wrong. This one, no. This one is already okay. Okay, now I want to get rid of the xy, right? Sorry, I want to get rid of the xy. So negative 2 times third plus first. Negative 2 times third plus first. Why did I do this again? So negative 2 times third plus first, right? So I get, this is negative 2xy plus 4y. Okay, so 4y minus 2. For the first one, copy the second one, and then the third one. Okay. Now I want to get rid of the this one. How do I get rid of this? I can do this. 2y minus 1, 2y squared minus y, xy minus 2y. I can just multiply by a half, right? I can just multiply by a half. Okay, now I want to get rid of the power. So I multiply a negative y by first plus second. Okay, so I will get 2y minus 1, negative y, and then I add, I got 0, right? Yes. So I get 2y minus 1, 0, and xy minus 2y. Now I can get rid of this xy by multiplying this by negative half x first plus third. Okay, so I get 2y minus 1. So I multiply this, I get minus xy plus half x. Okay, then I add, I got, I can do half x minus 2y. 2y minus 1, half x minus, oops, minus 2y, yeah. Okay, now what else can we do? Yeah, this y. Okay, so first plus second. We get 2y minus 1 and half x minus 1. Okay, you can, because this is already reduced until the single power, x to the 1. Okay, so you have reduced the original into linear. And if you want to write as this, or we normally will put in the form of y and x, you just multiply by 2. Then you can get to the single coefficient 2y and x. Okay, the coefficient is just 1. Is a Grobner basis. So actually, the whole thing is to reduce and using the first or second or third term to reduce the polynomial into a linear polynomial. Okay. And so this is a Grobner basis. I would suggest that you find some more examples, okay, for this. Go back and start from the beginning of the chapter to go through to see how they define the y less than x or x less than y, and at least 1 or 2 more of the example. But for this whole chapter, the idea is to find a reduced basis from the beginning. Okay, you will be given like 1, 2 to 3 polynomials in a set, and how you can reduce this to a Grobner basis. Actually, they are in the exercise that you can try. We can go over this exercise too, but try first. Okay, a single step division algorithm is you can divide, right? Number one, you can divide, single step division algorithm meaning reduction, one reduction to get a basis of smaller term order. Okay, the second one is to find a Grobner basis given polynomials. Number 3 is more or less the one that I showed before. The one that one is you can divide that the power, so it's reduced. And to find the algebraic variety, if the question is to find the algebraic variety, when you get to this, you need to solve this. So the algebraic variety for this one is when this is 0, this is 0, which is 2.5. Okay, so if you are asked what is the algebraic variety of this Grobner basis, the answer will be 2.5. The one that I solved before is, the answer is the line, right? The line through 1 and 2, right? 1 at the x-axis and 2 at the y-axis. Okay, so just only these 4 questions for Grobner basis, but I would suggest that you go through and find some other example. Okay, start back from the beginning and see how you can reduce. Once given, if you already can divide, you divide first and you reduce. If something like this that you cannot divide, like xy squared, x squared y, so you multiply 1 by y, 1 by x, then reduce, put them together and try to reduce until you get the linear factors. Then you'll get the Grobner basis. So the whole idea of this is, it's not unique, yeah? Your answer is not unique. So your friend might give me just this. Okay, didn't say that it has to be reduced until this, because the zeros for this and the zeros for this are equal, right? It's the polynomial that you equate to 0. So you will get the same algebraic variety. But some of you might use this different way, right? Some of you might multiply first to get rid, but I will use the one on the right to try to reduce. We first reduce the square, and then we also want to reduce the xy until we get a single x or a single y. All right. Any question for now? Like, yeah, I can understand it a bit. There are some parts that I have to study more. It's master, yeah. You're supposed to not understand all from class. Anyhow, okay. Are you okay?